Okay, so welcome to my session about GraalVM and its support for tools. I work on for Oracle Labs and on the debugger support in GraalVM. So the following is for informational purposes only. You should not make any decision on that. So first I will talk about GraalVM and the Polyglot world that is associated with that. I will explain Truffle AST interpreter, which is an essential part of GraalVM for languages. Then I will describe instrumentation for tools, how tools can plug into GraalVM, and we'll then have some demos where I will show how GraalVM works and how the tooling are look like. So GraalVM consists of several components. The core components of GraalVM is just-in-time compiler, which is an advanced, very efficient compiler that replaces C2 in JDK. Then it contains a Truffle framework, which is an interpretation framework for ASTs. Language are written as AST interpreters, and they provide the AST nodes to the Truffle framework where they are efficiently partially evaluated and compiled. GraalVM provides by default JavaScript integration at LLVM. It's a bitcode interpreter, but you can install other languages as well, like R, Ruby, and Python. The next component for GraalVM is SDK API. It's for embedders. If you would like to embed GraalVM into your existing application, you would use the SDK API that will allow to work with the GraalVM and run guest code on it, and etc. Then it contains Oracle JVM runtime, which adds Java libraries and garbage collector and things like that. And one part of GraalVM is ahead-of-time compiler. It's a native image generator which lets you compile bytecode to a native image. So you can create a native application from your Java application. And the advantage is that it's possible to compile also language interpreters. That means that you can create a native runtime that will execute JavaScript sources or other language sources, or all these combined. So here is in the picture what I was talking about. You have a just-in-time compiler that compiles the languages that compiles to bytecode, like Java, Scala, Kotlin. Then you have interpreters for a bunch of other languages, and all that is processed by GraalVM JIT compiler, and it's possible to embed all of that into OpenJDK, for instance, where you can replace the C2 with GraalVM JIT compiler. And we also provide Node implementation where V8 is replaced by GraalVM that allows you to run all the other languages in a Node as well. We are adding GraalVM into Oracle database. It's possible to add it into MySQL, or it can be run as a standalone application. So now what Truffle interpreter is. All language implementations are written as AST interpreters. That means that there is a unified AST representation in Truffle nodes, and all you need to provide a language integration is to write an interpreter that will translate the language source into the Truffle AST. Then Truffle cares about the specialization of nodes, partial evaluation, and completion. That all has the advantage that there is a very low overhead in language interoperation, because the AST representation is the same for all languages. That means that you can seamlessly execute one language from the other, as the AST is just one for all of them. Also, there is an instrumentation support built into the truffle, and it works on the AST level. That means that when you install an instrument, it plugs into the AST, and it can be specialized and partially evaluated with the code. So the instrumentation essentially becomes part of the code, and that means that there is nearly zero instrumentation overhead because it's all compiled together. And tools are attached as node wrappers to the AST. So again, here we see that in the picture. Initially, you will have AST nodes initialized. Then, depending on data that are flowing through these nodes, the nodes get specialized for strings, for double, integer, at whatever types are there. Or there is some generic representation. After that stabilizes, the truffle creates the specialized nodes, and then it's partially evaluated and compiled all together. How tools are plugged into that is here. Consider a node. That node is replaced by a so-called wrapper node that delegates to the original node and also to a probe node. That is something which can be used to attach the instruments. Here are several subscription nodes attached to that probe, and that delegates to client nodes that are provided by the instrumentation, by the tool that you want to plug in. So for instance, if you have a debugger and you submit a breakpoint, you select, you find the correct node which represent that part of the code, and you create a node that represents the breakpoint. And the breakpoint get a notification when the node is started to be executed. Also, when the execution of that node finished, it gets the return value, or when an exception was thrown from the node execution, it intercepts the exception as well. This, for instance, allows to have very fast conditional breakpoints, because the condition can be part of the AST and it's executed together with the code, so there is near zero overhead for the condition execution. The important thing for GraalVM tools is that they are language agnostic. They attach to the truffle AST, and they should not care about the particular language that the node came from. How it finds out where it actually should attach, or what the nodes are about when it cannot find language. Nodes have tags. When a node represents a function, it's tagged with a root tag. When the node represents a statement in the language, we have a statement tag for that. And similarly, for calls, for expressions, etc. So this is how tools find out what the node represents. Then the node have a source section information associated, the source file it came from, and line and column number information. So again, when you're going to submit a breakpoint to some line in some source file, you find that from this node information. And this all is language agnostic. So when instruments decide where to register, it finds it needs to define which tag and which source section it should attach to. This is declared in advance, and when the node is created, the instrument is notified about that, and the wrapper node is created about that around that node, and the instrumentation is attached. So in order to see how it works, I'll show you some demo. We start with cross-language debugging in Chrome. So I have prepared a few files in JavaScript, in Python, in R, and in Ruby. We can run all of that in a GraalVM. I'll show you the run script. We'll use GraalVM RC11, and we run a node with inspect when we will breakpoint at the first execution. So we'll attach Chrome to that in order to can use Chrome inspect, and here we'll see GraalVM is available to attach. Do you see that? Yeah. So we are suspended at the first statement here. It's a call to a weather method. This is a very simple sample application that computes weather regression model of from some cities. We have a database of cities and temperature of them. It's some artificial database, and you are going to create a regression model out of that. It started from Node. It's a JavaScript application, but to compute a regression model, it's not very convenient to do that in JavaScript, so we are using R for that. So we submit a breakpoint where the model is created. Maybe first I can show you that this JavaScript file is loading, if we step into that, is loading Ruby file. It's loading also R file, and there is some Python file written here as a string. So we can continue to that breakpoint where the model is actually computed. It takes some time to load the model and initialize the languages and so forth. And when the breakpoint is hit, we can step into that, and we are in a R source. Here you can see on the call stack that I came from JavaScript, and the JavaScript just calls the R function written here. If you look at the arguments, it gets some functions which came actually from JavaScript, which called this R function. So we can step through some R code for a while, and eventually we'll get into the place where the JavaScript function is going to be executed. When we step into that, we are back in the JavaScript, and we see on the call stack that from the JavaScript R was created and R was executed, and that called the JavaScript again. So the call stack shows you all the stack of the languages. Okay, we can go back to R. We can continue to the. Here you can see the local variables. So Chrome Inspector has fortunately no problem to show you R variables here. And if we get back to the JavaScript, we see the return value here. It's an R list, which is essentially an array, but it came from R, and R list. So JavaScript here gets some value from R, but it knows from the generic representation that it's an array, so it had no problem to find out the length of that R list. Because it's an array, it knows that it has some size, and JavaScript knows that length is a property of array, and it shows you return the size of that array. In a similar way, we can step into other languages. We have Ruby here, so we can step into Ruby. Again, we can debug the Ruby here in the Chrome Inspector. So no matter of what language is there, the tool is able to work with that. Here we can step into the Python script and again debug a Python script, including local variables and everything. When we are back here in the JavaScript file, we can look to the local variables. So for instance, here we see a function which came from Python and which has the Python description. We have a weather model from Ruby. We have cities from Java, city service Java object here, and there is a create model function from R. So we have all languages here available, all languages interpreting, and you can debug all of them at one place. So that's all from Chrome Inspector. The next demo is going to be some preliminary implementation of LSP. We have a preliminary integration with Visual Studio Code. So I will start an LSP server here.
So you're starting now with VM as an LSP server component, is that correct?
Yeah, this is an LSP instrumentation which is soon going to be a part of GraalVM. Currently it's in an experimental version, and it's provided for a so-called simple language. We have a testing language for GraalVM so that we do not need to deal with all the complexities of other languages, but this is something to test tools with and to showcase how GraalVM works. So at least you are sure that there are no existing language servers for this simple language. So it's served by this Graal LSP server. And now I will go to the VS Code client and run a sample application in Visual Source Code, Visual Studio Code. We'll run this LSP client here, the LSP client plugin, and it should open. Yeah, here it opens a sample SL file. It's written in the simple language, and it has connection to the LSP server. So for instance, if you select some variable name, it finds all the locations or places when the variable is read and when it's written to. This is provided by the language. The nodes are marked as that they are writing some variable or they are reading some variable. And from that, the LSP integration finds out locations of variables and if they are read or written to. There is also code completion, so you can see the local variables and the other things that you can call at that location. So this is a preliminary version of the LSP server. And the final demo is in NetBeans. Yeah, NetBeans GraalVM integration. Here I have NetBeans 10. It's the latest version that was released and late in the December last year, and it has a built-in support for GraalVM debugging. So I will run the demo that you already saw. It's here, but this time I will not run it with the Chrome Inspector option, but with standard debugging options. And so it's written on the address 8000. I will attach the Java debugger to that. And yeah, it does something. In order to see what it does, we pause that. Here in the main thread, you can see that it's doing something with Trefo nodes, so it's executing something on the GraalVM. And for GraalVM debugging, we have a special icon here that is relatively new. That's a toggle pause in GraalVM script. That means when you toggle that, it will suspend as soon as it finds out that some script is executing in GraalVM. So we can continue the execution and wait for this section to actually find this out. Yeah, and we are at the beginning when our script is executed. Here on the stack we see the JavaScript file, and we can do the very same debugging that you saw in Chrome Inspector here in NetBeans. Yeah, we can continue to a breakpoint. We can step into an R function. And here you see the local variables and everything. The advantage is that this is Java debugger. That means that you can switch from the script view to Java view. And here in the stack trace, you will see all the nodes that are executed and that actually interprets the language. That helps language implementers to see how the nodes they wrote were executed, and yeah, that provides the insight into how Truffle works. And you can see here also the probe nodes, the tools integration. Here the probe node was entered, and there is stepping node associated that comes from debugger. The node was entered, so we get onEnter event. We can step, and we were suspended on a step. So that's all from me. If you have some questions. Yeah, you were first.
What is the expected way to learn Truffle? Because I read everything on the Graal website, and I still don't understand half of it. Of course, you need to read some random papers like Truffle memory way out to understand how to structure it inside. Do you plan to write some comprehensive tutorial or something?
We are still working on documentation, and currently, unfortunately, probably the best way how to start out is to look to the simple language implementation and just see how.
Simple, really.
Yeah. Well, sort of, yes. Comparing to other language implementations, it's very simple. So, yeah, but we are working on the documentation, definitely. Yes.
Okay. I can help you use this.
Okay, you are welcome.
I had a question about the Chrome demo was very interesting because I'm wondering how you mangle all the different types from R, from JS, from you actually had a icon with C++.
Mm-hmm.
How does all this looks fine in the Chrome debugger, which expects, I think, JavaScript?
Yeah. Fortunately, it's quite tolerant because it also expects TypeScript or CoffeeScript or other languages. So they apparently do not have anything specific to JavaScript that they will blow up if they get another language. So this is why we can do that.
I mean, Ruby dictionaries, Python dictionaries, they are very different.
Yes.
Ruby has, the anchors, like they're not keys, they're actually static things.
Yeah, every object from every language provides its toString implementation. So we take the string representation from the language, how the language sees that object. But it's still language agnostic in terms of tooling. Yep.
If I understand correctly, the compiler is faster than the Java compiler, the just-in-time compiler. Are there any plans to improve the Java runtime to get as fast as?
There is a project to move actually the Graal just-in-time compiler to OpenJDK.
And it's faster than this? Is the standard?
In many situations, yes. Not in all of them, but in probably vast majority of cases, it's faster. Yeah.
Okay. And then we're planning to integrate it also in the JVM.
Yeah, this is sort of the plan. So we'll see how it works. Yep.
How do you manage to, for example, in Python integer can have an arbitrary size, in JavaScript there are only doubles. How do you manage to make it work?
In JavaScript, there are double.
You should repeat the question, sorry.
Yeah, so I'm sorry. The question was how we deal with types. For instance, in JavaScript there are doubles, but in Python there are other types.
For example, if I create a number, an integer in Python which is 1 kilobyte big, how can it fit in a JavaScript number?
JavaScript has big integers, so JavaScript can convert that to big integer. The idea is that there are primitive types which flows freely through languages, and there are object representations that when a language gets object from some foreign language, it delegates operations on these objects to that foreign language. So when it needs to find out a property of some object, it asks the object, give me that property. And it's up to the Python code to search the object layout and to provide that property. So if that object doesn't represent a primitive value, if it's quite long, it can delegate all the operations on this value to some methods on that object. And JavaScript that delegates that to Python.
Also, when you speak about Python, JavaScript, and Ruby, you mean that your own implementation of the translator of JavaScript source code, the Python source code to the AST Graal,
Yes.
which means that every time, for example, they add a new keyword, a new feature to any of those languages, you have to keep up with the
Yeah, definitely. The languages need to be updated with the latest version. So, for instance, in JavaScript or in Node, when there are some new features added, we need to keep up with that. But it's not that hard, because all that we need to upgrade is the interpreter, not the runtime or other things, just the interpreter, and that's it. So that allows us to bring new JavaScript features faster than V8, for instance.
And same way, I guess that it's not possible to use, for example, in Python, there are many libraries in C Python at least that have C bindings. I guess that's not possible to use them, because it's just possible to use your Python code.
There are some libraries distributed with the languages. For instance, in R we have many libraries redistributed, and regarding Python, I'm not really sure, but we definitely work with NumPy, or have some integration with NumPy. So, yeah, these languages are not in final state yet. JavaScript and LLVM is final; it's complete. But these other languages are in progress. They are mostly complete, but not 100%. So, yeah.
Time for
Yes.
one more question. Yes.
So, if you, when would you probe your debug probe, for instance, is it possible to change the tree as in hot code replace, basically, by this method, and regenerate the tree? Let's say you modify a function in JavaScript.
Yeah. The question was, when there is a probe, if it's possible to replace that when the code is modified. Yes, the instrument can freely attach and detach, and then we transfer back to the interpreter mode, change the nodes layout, change the AST, and then after that stabilizes, it's compiled again. So yeah, there is just the optimization at that location. The nodes are changed as they need to be. For instance, if you remove a breakpoint, the breakpoint that represents the node is removed, so the node structure changes. So it's transferred to interpreter mode, and then after it stabilizes, it's partially evaluated again and compiled again.
Thank you very much. Very interesting.
Okay.